Okay, I think we're on. Okay, well, hello everyone. We are back for another season of error theory seminars. So I guess we took quite a long break during the summer, but now we are going to have like a series of like presentations. And to start, we have Dorian Baudry who's presenting today, and he's going to present his work that got accepted as an oral paper at NeurIPS. So if you're in San Diego next week, don't forget to visit him at the poster and the oral presentation. And so Dorian is currently a researcher at INRIA Grenoble, where he works on sequential decision making problems and specifically in bandits. He completed this work while he was still a postdoc researcher in Oxford with Patrick Rebeschini and his group. And previously, before that, he was also a postdoc at NSAE with Yann Perché, and he did his PhD at INRIA Lille. So thank you for accepting our invitation, Dorian, and the floor is yours.
Okay. Thank you very much, Antoine, for the kind introduction. And first of all, I want to thank the organizers for inviting me to start this new seminar season. And I also want to thank you for keeping this very cool seminar going with the years, like always very interesting talks. So yeah, as you said, I recently joined INRIA Grenoble in the GHOST team as a researcher. And the work I'm going to present was done during my postdoc with Patrick Rebeschini at the University of Oxford. And I will be very excited to present this work next week at NeurIPS in San Diego. So if some of you are there, and if after this seminar you still have some questions, some ideas or some thoughts about this project, feel free to come and chat next week. So the title of this work is Does Stochastic Gradient Really Succeed for Bandits? And as the title indicates, this is actually a follow-up of some recent works on stochastic gradient algorithms analyzed in the context of bandits. And so when I started my postdoc with Patrick Rebeschini, he mentioned to me those quite recent works. So one of them is 2023, the second one is 2024. And when I read these works, I was quite intrigued by such a simple algorithm was still not so well understood. And I found the insights from these works very interesting, intriguing, and surprising. So I wanted to investigate a bit more, especially since there were still quite a few open questions from these works. So this was really like the beginning of the project. So now let me introduce more formally the setting and why we are considering this kind of problems. So first, I guess that you all agree that gradient-based approaches are quite a very popular and powerful tool in machine learning. And in reinforcement learning in particular, approaches based on the policy gradients have been very popular in the past and in practice. So I guess I don't have to spend a long time in introducing reinforcement learning to this audience. But essentially, let's just say that a common recipe to tackle reinforcement learning problems is to parameterize a policy by some parameter theta, and to model the expected reward that the agent is going to collect as a function of this parameter theta. And so then a natural approach to apply the policy gradient principle is to just use a gradient ascent to maximize this function j of theta. So this is a very old and natural idea. So the class of policy gradient approaches. And so the motivation for studying is this kind of algorithms is that they are very popular in practice. So you know that in deep reinforcement learning, a lot of approaches are based on policy gradients. But to these days, we still have quite limited theoretical understanding on those approaches. And so the idea of this project is that, and this line of research in general, is that achieving better theoretical understanding in simpler settings is valuable. And so, as I said, this work is a follow-up on recent works on, more precisely, softmax policy gradient in the context of multi-armed bandits. So just to recall some notation, my notation about the multi-armed bandit problem. So let's say that an agent play for some time steps t, and at each time step, the agent must choose an action, at, from a set of k actions. Then the agent will receive a random reward, rt, that is drawn from a distribution associated with the action at. So we are considering the context of stochastic multi-armed bandits. And so the key problem in this setting is that we have no observation for other actions than the one that is played. So the objective is to maximize the accumulated sum of rewards, given that the distributions are unknown at the beginning of the interaction. And so we are facing the classical exploration-exploitation trade-off. So this was just to give my notation for this problem. So we understand very well some approaches for bandits. So popular approaches are, for instance, UCB algorithm, so optimism in face of uncertainty for frequentist approaches, and Thompson sampling for Bayesian approach. And so we know that well-tuned UCB and Thompson sampling algorithm can achieve optimal guarantees in multi-armed bandits, especially asymptotically optimal guarantees. We understand them very well, but the problem is that if we consider more structured settings in reinforcement learning, it is not always very practical to extend those approaches. And on the other end, we have the policy gradient approaches, which are like very popular in practice, but generalize very well to structured settings, but we still have limited theoretical guarantees. So yeah, the goal is to study policy gradient in multi-armed bandits in order to get some insights about those methods and possibly to guide generalization on those approaches. So now I'm going to introduce more precisely the algorithm that we consider in this paper. So again, we have k arms with reward distributions nu k and means mu k. And so we consider a policy that is a mapping of past rewards and actions to a probability to sample each arm. So we denote the probabilities by pkt, the probability to play arm k at time t, given all the past information. And so by doing a policy gradient, what we want is to maximize the value of the policy, Vt, which in this simple multi-arm bandit problem is just the sum of the probabilities of each arm multiplied by their average. And what we want to do is to perform gradient ascent on this value Vt. So to obtain a probability from a parametrization, we consider some parameters theta, so theta k for each, we value theta k for each arm k. And the sampling probabilities are just going to be the softmax transform of those parameters theta. So pkt is exponential of theta kt divided by the sum of those exponentials. And so if we compute, so we can now compute the gradient of the value of the policy with respect to this parametrization theta. And we just obtain pkt for arm k multiplied by mu k minus vt, which is just the advantage function of arm k with respect to the current policy. Okay, so very simple formula. And it's just a few lines of computations. So if we want to do a gradient ascent, what we are going to do is just update theta k as the previous parameter plus a learning rate eta that we're supposed to be constant and multiplied by the gradient, so which is the value that I introduced just before. The problem is that, of course, we don't know the averages. Otherwise, we would already have solved the bandit problem. And we don't know also the value of the policy. So we have to estimate this gradient. And so a typical estimate that is used in the literature is the estimate that I put in this slide. So it's just like very straightforward to show that this estimate is an unbiased estimate of the gradient. If you compute the expectation of of this estimate, you exactly get the gradient of the value of the policy. And so with this update, we obtain the stochastic gradient bandit algorithm, which is just softmax policy gradient plus this stochastic gradient estimate. And this algorithm is actually very old, since it was it can already be found in the Sutton and Bartow book of reinforcement learning. And it can be like very easily implemented, because you see that it's just like very simple update of parameters and just computing a softmax transform. And at each step, sampling a norm according to the probability distribution given by the softmax transform. So very, very elementary algorithm. And the only parameter is actually the learning rate eta. So if we compare to typical bandit approaches, we see that this policy is very different, because if we compare to upper confidence band algorithms, for instance, we see that for a UCB, if we have access to the empirical averages of each arm that I denote by mu kt, and the number of counts nkt, you can easily understand what the algorithm how the algorithm is going to play. If you also consider Thompson sampling, for instance, in the Gaussian case, the policy is again fully characterized by the empirical average and the number of counts of each arm. So this makes the analysis of those algorithms almost entirely based on considering some events about those statistics. So now, before continuing, I'm gonna introduce some assumptions about the reward distributions. So we assume, without loss of generality, that the arm 1 is the optimal arm. And we also assume that the rewards are bounded in -1, 1. And so for to analyze the performance of SGB, two metrics have been considered in the literature. The first one is asymptotic convergence of the algorithm. Can we show that SGB converges to the optimal arm? And the second one is the regret, so which is like the standard definition of regret in bandits that I wrote in this slide as a function of sampling probabilities. And so we know in bandits that we can get a regret that is logarithmic with inverse dependence on the gaps, suboptimality gaps, and that can also be bounded by a square root of kt. So now to detail a bit the related work, so I'm gonna introduce the results presented in the papers that I mentioned in my introduction. So earlier result is that softmax policy gradient, but implemented with exact gradient, okay, so which assumes oracle knowledge on the problem. So softmax policy gradient converges at a rate inverse of t. So in particular, this gives a logarithmic regret. But in this setting, we assume some knowledge that we actually don't have in practice. So more recently, in the paper Stochastic Gradient Succeed for Bandits, the authors show that SGB converge at rate inverse of t, but for learning rates that are smaller than essentially delta squared, where delta is the minimum gap among all arms. And under this assumption, the authors obtain a regret bound that is 2 log t divided by eta. So this is very interesting results because it shows that SGB can achieve logarithmic regret if the learning rate is small enough. But unfortunately, this result is not entirely satisfying because delta squared can be like very small in practice. And so this does not really give a practical tuning for the algorithm. And later, the same authors extended these results, showing this time that the SGB policy converges to the best arm for any constant learning rate. So you have asymptotic convergence, but this time there is no anytime valid rate of convergence. So this gives a very natural question, which is to ask if SGB actually achieve logarithmic regret for any learning rate. Do we have logarithmic regret even for large learning rates? And if it's not the case, can we characterize some regimes of regret according to the value of the learning rate? So this is the question that we tried to tackle in this paper. So now let me introduce a bit why analyzing SGB is difficult, and so which is the reason why we didn't get results before, like until very recently. So if we try to apply the classical tools from the optimization literature, we encounter some difficulties. First, the objective function is smooth but is non-concave. And also, we don't have a PL inequality. And in particular, the previous works used a weaker version of the PL inequality. But this trick requires some assumptions on the inverse probability of the best arm. So the final results depend on the expectation of the inverse probability of the best arm. And a last property that makes the problem difficult is that the gradient vanishes near any one-hot policy. So when the algorithm starts converging to to putting all probability in one arm, then the gradient vanish. So now let me introduce the main contributions of this work. So the most maybe spectacular guarantees we get is actually unfortunately restricted to a two-armed bandits. But in this case, we can fully characterize the regret of HGB. So in particular, we showed that if the learning rate is constant but smaller than the gap delta, then the regret is logarithmic for any problem with gap larger than delta. So we get a regret log t divided by 2 eta in that case. And then for learning rates larger than delta, we could prove that there exists a bandit problem for which the regret is polynomial. So we get a bound that is t to the eta minus delta divided by eta. So we see that getting a learning rate that is close to the suboptimality gap is really essential. Because if you get a learning rate that is a multiple of the gap, for instance, if it's 5 delta, then you get a rate that is t to the 4/5. So this can go very arbitrarily close to 1 if we completely misestimate the suboptimality gap. And for more than 2 arms, we only come with a conjecture that we support both by experiments and some preliminary theoretical results. We think that there exists the same critical regime effect. So the critical regime will be eta to be 2 delta divided by k. And that if the learning rate is smaller than this critical rate, then the regret is k minus 1 over k log t divided by eta. And similarly, we think that the regret is polynomial, can be polynomial above this rate. So now I will introduce a bit some of the tools that we develop in the paper to show those results. So first, a novelty compared to previous works is that we propose a new regret upper bound to analyze this SGB algorithm. In particular, we use the expected value of the parameter of the best arm, theta 1, and we use that theta 1 is related to the probability of arm 1, P1, so P1, 1 minus P1. And so this way, we can decompose the regret as a sum of 2 terms, with the first one that is the expectation of the parameter of the best arm divided by eta, and the second one that is the expected value of the sum of 1 minus P1 squared. So we get the expected value of theta and 1 minus P1 squared term. And we can actually interpret those terms. The first one, we call it the post-convergence term, because in the paper, we show that the expected value of theta 1 is no more than logarithmic in t. So this term is the one that gives the log t bound when the algorithm is guaranteed success. So success defined by logarithmic regret. And the second one, we call it failure regret, because it is a term that can explode if the regret is not logarithmic. And we relate it to the probability that the algorithm fails to converge to an optimal arm within the horizon T. So a first result, a first more precise result that we give in the paper is that we show that for any learning rate eta, the expected value of θ1 is bounded by log T. So essentially, as I said, this post-convergence term in the regret bound is always logarithmic. And this is true for any learning rate, which means even if the learning rate is very large, this still holds. So in a sense, the expectation of θ1 quantifies the regret of SGB in a good regime where the probability of the best arm is converging to 1. And this confirms some previous results in the literature. So the proof is, in the two-arm case, the proof is very elementary. It's just based on some application of Jensen inequality. And then we just use like a first-order expansion, a second-order expansion of exponential. And we just get like we get a recursion formula that just gives a log T bound. Okay, but in the case for where there are more than two arms, the proof is a bit more sophisticated. So this result shows that to get the regret guarantees of SGB, we only have to analyze what we call the failure regret. So this expected sum of squared probabilities. So in the paper, we explain that those probabilities are related to the number of times the algorithm stays in a regime where the probability of the best arm is underestimated. So it is, in a sense, the expected duration of a transient regime when P1 is smaller than any threshold, basically. And so if this term is large, there is a large probability that SGB is stuck in a local suboptima. Okay, and so the reason why we were able to get regret guarantees for two arms is that we were able to exhibit a potential function, so which is so that we call xt, which is 1 minus pt over pt. So here pt is the probability of the best arm. I just dropped the index 1, and we showed that this function exhibits a recursion formula that directly involves the 1 minus pt squared terms. So essentially, simply by telescoping, we are able to prove that if eta is smaller than delta, then this expected sum of squares is bounded by 1 over 2 eta delta minus eta. And what is interesting to remark here is that this recursion is an approximation, and it's an inequality, but it's very close to be an equality. So with this delta minus eta term in this equation 3, we can actually imagine that if eta is larger than delta, things can go badly, because we would have that the expectation of xt is increasing. And since xt is essentially 1 over the probability of the best arm, then we would have as 1 over the probability of the best arm can go to infinity in expectation. So we see that something might go wrong in the algorithm. And so this is why we started to feel that we should be able to prove a negative result when eta is larger than delta. So if I complete the analysis for two arms, so the final regret bound we get is RT is smaller than 1 over 2 eta log t, essentially, plus this constant term 1 over eta minus delta. So this is the complete regret bound for two arms. Okay. So now, to have a break from the analysis, let me show you some experiments that seem to confirm those theoretical findings. So essentially, the difficult problems we could get in our setting would be essentially Rademacher variables. So because we are in -1, 1, so a Rademacher variable is giving a -1 or 1, just like Bernoulli, but for the range -1, 1. So we have Rademacher variables with averages near 0, which is like the highest variance you can get in this range. And so we tried SGB with different learning rates. And so on the left side of this figure, we can show some regret curves for learning rates going from delta over 2 to 5 delta. And what we see is that for the learning rates that are validated by your theory, which are delta over 2 and delta, we have average regret that is like have a logarithmic curve, but also the 10, 90% percentiles are very like centered. Sorry, the empirical regret, the average empirical regret is very centered in the 10, 90% percentile. But if we take larger learning rates, 2 delta or 5 delta, then we see that the empirical regret grows seems to grow faster than logarithmic, but also the percentiles start to explode. So for instance, if we look at the worst trajectories, we see that a significant number of trajectories have linear regret. So this is what we have in the right side of this figure. So in the table, we see that for a learning rate that is 5 delta in this setting, after 5,000 interactions, we have 20% of trajectories with regret larger than T delta over 2. And this will be the regret of a uniform policy that chooses at random. And even after 20,000 trajectories, we still get 15% of trajectories with linear regret. So we see that this number does not decrease very fast. Okay. So now back to theory. I want to talk a bit about how we got this result that the learning rate can be polynomial with the regret can be polynomial if the learning rate is larger than delta. So what we showed is that there is an instance which is, so imagine that the suboptimal arm is just deterministic. It gives you 0 reward. So in that case, when the suboptimal arm is played, the algorithm is not updated because the updates are just multiplied by the reward. So if you have 0 reward, you have no update. And it is the optimal arm that is randomized. And in particular, it is a Rademacher variable with average delta. And so what we show is that if eta is larger than something that is very close to delta, then the regret is polynomial, in particular, because the probability that the regret is linear is a function of t to the minus delta over eta. And so the regret bound is just the lower bounded by the probability to have linear regret multiplied by t. So what this shows intuitively is that when things go bad for SGB, they go really bad. Like we can have a probability of linear regret. And if the learning rate is smaller than delta, this probability is too large to compensate for the linear regret. And this is how we get polynomial regret. So if we get a bit into the technical details, so as I said, because the second arm is deterministic, the parameters only change when the first arm is pulled. So the first arm, which is the optimal arm. And essentially what we show is that it only requires a logarithmic number of unlucky pulls of the best arm to make it not played again before the end of the horizon. So if I have log t divided by 2 eta delta rewards with average around minus delta, which happens with some probability that we can get from concentration results or anti-concentration results actually, then we never play the best arm again before the end of the interaction. And this is how we prove linear regret with some probability. Okay, So now let me introduce, so yeah, that's all for the technical results of the paper. So to conclude this presentation, I want to introduce some open problems. So first of all, you saw that we almost fully solved the problem for two arms up to the very special range around delta, because we have some second order terms in our results. But the question is now, can we extend this for more than k arms? And so as I said, we have a strong conjecture from the analysis presented in the paper that the learning rate, that is the critical threshold for k arms, is 2 delta over k. And also that the regret in that case would be k minus 1 over k log t over eta. So what remains to do to prove those results would be to improve our upper bound on the expectation of theta 1t. And but more interestingly, to find techniques to upper bound the failure regret for more than k arms, because unfortunately for k more than 2 arms, sorry, because unfortunately for k arms we don't have a nice potential function that exhibits like good properties as what we had for 2 arms. So this is an open direction. So in the paper, you can find some empirical support for the regret bound that we conjecture. So we conducted quite a few experiments where we plot the asymptotics of the regret, and we show that this matches k minus 1 over k log t over eta in a variety of settings. So this is some empirical support. And we also have some empirical support for the fact that the critical learning rate is 2 delta over k, because in a well-chosen experiment that we designed to be difficult for SGB, inspired by our lower bound proofs, we show that the distribution of the regret can be bimodal, and in particular that the two modes correspond to the two terms that we exhibit for our regret decomposition. So this is the right-hand side of the plot that I present here. So for every learning rate, so for instance, if you take the purple learning rate, so which is the highest that we choose, it's 5 delta. We have a first mode of trajectories, which are at log t over eta, with very low regret. But we also have a second mode with a lot of trajectories with linear regret. And we see that for this learning rate, this second mode is very significant. It's again like 25% of the trajectories that have linear regret. But the more we decrease the learning rate, so we increase the value of the first mode, the logarithmic regret, because it's inversely proportional to eta. But we also significantly reduce the magnitude of the second mode, which characterize failure. So we see that for the red learning rate, so delta, we have like still a quite significant proportion of failure. But then if we go to the learning rate that we believe to be below the critical threshold, so the yellow one and the blue one, so 2 delta over k and delta over 10, so which is delta over k here, we see that we actually cannot see the failure mode in our plot. So essentially, the number of trajectories that fail becomes so small that we don't see it in our experiments. So yeah, so this makes us really believe that for the regret of SGB, we can the decomposition that we propose really represents what's happening in practice, with a logarithmic term for some successful trajectories, for the proportion of successful trajectories, and another term which could be just t multiplied by the probability that the run fails within the time horizon considered. And we believe that this is how this algorithm should be analyzed in terms of regret. So yeah, so maybe I'm gonna just skip this part. So yeah, in the paper, we propose some discussions about how to possible directions for future analysis. But yeah, now I'm just gonna briefly summarize the content of this paper. So as you can see, we improve the theoretical understanding of SGB, especially in terms of regret analysis, because the convergence, asymptotic convergence, was well understood by previous works, but we improved the regret analysis part by extending the range of learning rates for which we can get regret guarantees. And we think that there are still a lot of things to understand about this algorithm. So first of all, some theory has to be done for the case where there are more than two arms, which is actually not easy. Like we have to prove all the conjectures that we showed in this presentation. And of course, later the goal would be to extend those analyses to other natural variants of SGBs. So in the literature, the MDP variant has been considered, or there has been also some work about alternative, about structured policy, more structured policy parametrizations. And also a question that we can ask is this softmax parametrization the best thing we can do for this kind of gradient ascent algorithm in bandits? Like if we consider other families of policy gradient algorithms, could we obtain similar results? Would we still have a similar regret decomposition with some kind of post-convergence term, some failure regret? It's yeah, those are the open questions. And so if some of you are interested in working on this topic, feel free to reach out. Feel free to come talk to me in NeurIPS. And also I think that Patrick Rebeschini has some funding for visiting our postdocs in Oxford. So if some of you are interested, feel free to apply. And that's all for my presentation. Thank you very much for your attention.
Nice. Thank you.
Thank you. Nice presentation. You have a bunch of questions / comments, I guess, pretty high level.
Yeah.
Yeah, so interesting. So it's kind of like, in a way, surprising that such a simple method could even do anything on an exploration problem, even though it seems to be somewhat limited. But it's still just policy gradient, and you're doing nothing with it. And just choosing the step size not to be too large. So should we expect methods like this to do well more generally? So what is the long-term forecast for simple methods like this? Can we push these methods? So like first specifically, if we just take literally this policy gradient approach and just think about how to choose the step size, I guess you talk about that the step size needs to be pretty small compared to the smallest gap, not to see some big regret. But I suspect that that's maybe a little bit conservative or kind of worst case-ish, right? So maybe can you walk us through of whether you expect a large regret, like this delta over k limit seems to be like very restrictive. One would think that, well, if there are many arms, there are some small gaps. You definitely, in a finite interval, do not want to compete with the arms. Like deciding between the arms between which the gaps are really tiny for given a finite amount of interaction and samples is not going to work anyways for anyone. So one shouldn't, like, if we take this finite, I don't know, horizon approach, then one natural thought would be that, well, maybe you split the arms between those that are kind of equivalent to the best arm, but statistically indistinguishable, and like do something with the analysis. Would something like that be possible to do for this algorithm? And then could you hope to get some better guarantees than what you're currently conjecturing are possible?
Yeah, that's a very good question. So, first of all, in the paper, we also consider time-dependent learning rates. And we show that if you have absolutely no idea about the gap, you can still use 1 over square root of t, and then you get square root of t regret. So this is something
Right.
that... So then there is this kind of recipe, like, okay, if you expect the problem to be difficult and you have no idea to which extent, maybe you can just use a time-dependent learning rate, and it can work. But actually, yeah, this is a very good question, because we have this threshold for the theoretical guarantees, but still, in the analysis, we don't get like a fine decomposition about what's happening for each suboptimal arm. So it's difficult to say, okay, maybe if we have one arm that is very close to be optimal, we can essentially consider that it's not a problem to play it. But we don't have an arm by arm decomposition which would make this thing appear in the analysis yet. So I think it's a nice direction to try to get to this level of granularity in the analysis, to be able to say, okay, I have arm-dependent regret bound, essentially, arm-specific regret bound, and I can say, okay, the very suboptimal arms, I'm going to rule them out anyway. And if I play a suboptimal arm, maybe I would... It must be an arm that is not so bad, which is like what you mentioned. But I think this would imply to finally upper bound the probability of commitment to each arm. So saying, what is the probability that an arm K is played more than alpha suspect, essentially. And if we are able to get good bounds on this kind of probabilities, then maybe we could have the level of granularity that you express. But I agree with you that what we show is that there is a probability of failure when the learning rate is too bad, but failure does not happen with arbitrarily bad arms. It appears with arms that have a gap larger than the learning rate, and so smaller. Sorry,
smaller.
So it's true that we could also, like, for practitioners, we could also say, maybe if you have a setting that would be like, I don't know if you're familiar with satisficing bandits, or like, but essentially settings where you say, okay, I want to be good up to epsilon, and you give some, if an arm has a gap smaller than some epsilon, you say, okay, it's not suffering regret, I don't care about epsilon gap. Then maybe if you tune the learning rate to be epsilon, you get guarantees for this setting, like logarithmic regret guarantees for this setting. I don't know. And this is something I would like to explore, but it's not so clear how to reach this kind of guarantee.
Yeah. In the meanwhile, I want to tell people on the call that you're also free to ask questions. Of course, I do have more questions. So in the meanwhile, while people are thinking about the questions, here's my next one. So you already showed this bimodal distribution and whatnot. Something similar, by the way, is happening with UCB as well, right?
Absolutely, yeah, absolutely.
Documented in the literature that, like, this is not so surprising. You make UCB very aggressive, meaning that you try to minimize the expected regret. Then it becomes really risky, and it like the expected regret is minimized by concentrating the regret around its minimum value, but moving most of the probability mass to zero, like no regret at all, and then leaving a considerable mass on the worst arm or worse arms if there are multiple of them. So it's not really completely unfamiliar.
Absolutely,
it's kind of a sign of aggressive tuning of an ergotam.
Absolutely,
Related question to this is that, we should care about the high probability bound on the regret or regret concentration, right? Because it's fine to think about that, expected regret, I care about minimizing my expected regret. But if tail of the regret is really big, then maybe you will not like that algorithm at all, right? So if occasionally that algorithm, and not too rarely, like rarely enough so that it matters, it gets stuck with a really bad situation, and you achieve this at the expense of, like most of the time, though, it's like in really good situation, maybe altogether you don't like it because we are a little bit risk averse. Like you run an experiment, really expensive on some simulator, big time, whatnot, big data, and the outcome is just could be bad. So that you want to be risk averse. So any thoughts about this regret concentration, like how this plays out in this case? Have you tried to look into this and understand this beyond the expected regret?
Yeah, that's a very good question. So actually, yeah, like this regret decomposition really shows that it should be possible to bound the probability of failure and to say, okay, if this does not happen, then you have a good logarithmic bound. So, but this would need like a very, very precise bound on the probability of failure, which we maybe do not have now. But I think due to the behavior of the algorithm, it could be like super nice to be able to say, okay, I want a probability 1 minus delta to get logarithmic regrets, and be able to tune the learning rate according to this probability and say, okay, now I have a learning rate that is able to guarantee this. And yeah, this is something that could be really interesting. And just to come back to your discussion about the bimodal distribution, actually, during the reviewing process, we had a very nice discussion with a reviewer about this. And so we included some references about past works that discussed this kind of bimodal distribution for UCB algorithm by Jean-Yves Audibert and his group. And I also want to say that regarding this discussion, what we can see is indeed what would happen also if you consider the UCB or Thompson sampling algorithm that would be badly tuned. So for instance, imagine you take a Thompson sampling, but you like Gaussian Thompson sampling with non-variance, but imagine you underestimate the variance, for instance, then I'm pretty sure you would observe exactly the same kind of regret curves, where when everything goes well, the algorithm converges nicely and has logarithmic regret. But if there is bad luck, then the algorithm could rule out the best arm with some probability. And so
and it
essentially, sorry?
And then it takes forever for it to recover.
Yeah, and then you get linear regret. But this is the drawback of algorithms with logarithmic regrets, is that logarithmic number of samples is not so big. So if you get unlucky sample logarithmic number of samples, then you can just get stuck forever.
Right.
And this has been documented in the literature, indeed.
I see. So that's a very clean explanation with this log T samples on an arm that you're constantly eliminating. You try to keep it like that. And then, of course, if you were unlucky, then it will take a long time, exactly because you're forcing the logarithmic regret. That was a very, very clean, very nice explanation.
Yeah.
Good. So next question, maybe last one from me. So pushing the limits of these algorithms, going to MDP land. Is that a no-no for these algorithms? You have to do something substantially different, or you think that you can just like roll, and like how would you do that? Have you thought about this? You must have.
Yeah, of course, this is a very natural extension of this work, but so it has been shown in the literature, in some of your papers, actually, if I remember correctly, that for MDPs you have a slightly different measure of complexity, which depends on other parameters of the MDP. So it's not just the gap. So I would just assume that there would be like a similar regret guarantees, and in a similar way, you would have like some critical learning rates that would depend on some complexity measure of your MDP. But yeah, I'm not so sure about how it would generalize exactly. especially maybe further assumptions will be needed on the transitions, or I don't know. It's not so clear
it
to me
seems
yet.
to me that like I would be a little bit skeptical about the success of transferring these results to MDPs without more substantial modifications, because in bandits it's you can be optimistic about values and then you will be fine. In MDPs you have to be optimistic about action values. So if you somehow can bring that in, then it might work. But if you don't bring in kind of action values and like the aspect of that, like you need to plan to explore in MDPs, that is the job that is done by the action value functions, right? Like they do the credit assignment or whatsoever. And so, yeah, I'm not exactly sure whether if we just try to apply, I don't know, reinforce like that, proper learning rates, things would go well. Also, not talking about the gaps in MDPs. Yeah, like everyone always says that like they're tiny, and of course, like they could be sketches, and so it's like, yeah.
But if I remember correctly, you have a newspaper about the asymptotic convergence of reinforce for any learning rates. So
sure, but it's not talking about regret, right?
Yeah, it's just convergence.
To just talk about whether things are gonna eventually work out, or whether they work out well.
Yeah, I see.
Here, I'm more trying to poke in the direction you were going, which is like, do we get good regret? Before we go, so you mentioned this 1/√T learning rate, which is really nice. But I wonder whether in this case the algorithm becomes like overly defensive. It's like then the regret really goes up to √T. Even like after a long time, it still grows like √T.
It does. Yeah. It does, because the √T still comes from the log T over eta bond. And so you are the bimodal distribution that you see in my plot would be, the first mode would be centered in √T log T. Yeah, of course. Yeah. So you would actually see that the good trajectories would be exactly giving √T regret.
Yeah. So, I mean, in a worst case sense, √T is optimal, but of course, people like to play this best of both worlds games. You would want to go beyond that. I don't know. What does it mean for practice? Like, wouldn't it be just like, anyways, like in practice, all these gaps are tiny, so √T is the best that you can get, and so let's just run these algorithms even in MDPs with 1/T. Like, is that a reasonable? So maybe
I don't know, but I think something that would be very relevant in practice would be to be able to say, okay, if things go wrong, then you're gonna pay only arms that have a gap smaller than eta. And this way, people can tune eta according to what kind of loss they are willing to suffer compared to the optimal policy. And I think this can give, if we can achieve this kind of analysis, I think it would be like of practical relevance. Yeah.
Cool. All right. Very good. I don't have any more questions.
Thank you. Yeah.
Thank you very much for your questions.
I just have a simple question. Actually, sorry that I didn't in the Google Meet. I just didn't find the chat. I just want to type in the chat, but I didn't find it as previously. So
it is there. I don't know how you're not finding it. It's like this little like icon with like a little bubble kind of thing on the side on my screen.
Oh, I'm not sure why on my side. Anyway, okay. So I just double check the S. So in the for small step size eta already, it can achieve like a logarithm. SG can achieve logarithm regret. Is that the optimal rate?
Yeah, that's a good question. So okay, let's talk about two arms. We have this regret log t divided by 2 eta. Okay. And it's actually optimal if we choose eta to be very close to delta. Okay, so essentially, and the bond is matched. So it matches the Ley-and-Robbins lower bound. If you take Rademacher variables with like very, very small gap and the averages that are very close to 0. So this shows that you cannot improve this result if you have something that is just a simple function of eta and delta like this.
Okay, so this is for two arms album. Like for multiple arms, do you think we can like improve the speed of SGD?
No, I don't. No. Again, I think this rate k minus 1 over k log t over eta is unimprovable. Otherwise, you would break the Ley-and-Robbins lower bound, and so essentially you would have worse guarantees on some instances.
Actually,
this is actually. Yeah, sorry to precise a bit. This is actually another argument for the conjecture that the learning rate is the critical learning rate is 2 delta over k, because it is the learning rate that matches the Ley-and-Robbins lower bound.
Oh, actually, I don't mean the learning rate. I mean the SGD algorithm itself. Do you think? Okay, I just ask about the general knowledge, not just about your paper. Okay, so do you think like the SGD can be just improved in some way? For example, like variance reduction, etc. To okay, we can't improve if we can't improve the rate. How about do you think we can like improve the critical step size or improve the like a bound, for example, like C log T, improve the C? Do you think is possible?
Okay, yeah.
By just adjusting the algorithm.
Yeah. So if you use, so for instance, so here the results are really using the fact that the update of SGB is using like just one sample estimate of the gradient. So a common technique to analyze a policy gradient algorithm is to just estimate the gradient using batches of observations. And so if you use batches of observations, then you reduce the variance. And if you reduce the variance, you could increase the learning rate accordingly. But the trade-off between the two is not so clear because, of course, you need to pay a bit more to collect a batch of observations.
Yeah.
So would you... I don't know if there is like some kind of optimal trade-off to find between reducing the variance, increasing the learning rate in terms of regret. I don't know. This is an interesting direction.
Okay, cool. Thank you. Yeah.
Artem, so you had a question. Do you want to unmute? I don't know if Artem is still here.
If he doesn't want to unmute, I can also just read the question. Basically, Artem says that, okay, good learning rate requires knowing this optimality gap. So do we know of any settings where somehow this knowledge of optimality gap would be available, like maybe some specialized problem or something, or how to think about this? I guess like that's the wider question, but
yeah. And his question, I think, is also related to could we also maybe estimate delta to tune SGB? And actually, I have an answer for this, which is that estimating the gap is just as difficult as solving the bandit problem. So basically, you would, if you want to do that with enough statistical guarantees, you would just suffer more regret to do that than the logarithmic bound that we get. So yeah, this is not something that is that sounds reasonable to do. So it just requires very strong expert-based knowledge, maybe, or I don't know. I don't have a specific application in mind, but maybe some cases you know that some arm is gonna stand out in a way. I don't know.
Can't you like maybe you can't estimate the gap for all the arms, but you can definitely estimate some gaps between the arms that are often taken, and for the rest, you're like, okay, I don't have enough data for those, so those gaps might be probably small, and just based on what you can estimate, go with that?
Maybe, yeah. Actually, maybe you could use like a 1/√T learning rate at the beginning, and then try to refine.
Right, like maybe stop. Maybe like you want. Okay, you can decrease the learning rate slowly like this, and then this gives you some data for a bunch of the arms. And maybe you want to stop this decrease of the learning rate at some level. Like that's like ideally if you had the data in mind, you can do that, and somehow you can slowly, gradually do that without losing that much. Yeah, it might be possible to do
Might be
something.
possible. It's not clear what you would sacrifice by doing this. I don't know. Yeah.
One question though I would have is that, okay, like is it going to be very specific to bandits? Because if it is, then it's like, yeah, it's not too valuable. If there was a general, I don't know, learning rate tuning mechanism that you just like throw on this thing, it measures some variance and whatnot and some statistics, and then you mentioned that it's more broadly applicable, then maybe that would be more useful. You definitely don't want to just have a result just for bandits, although it's a good start, but
Yeah, of course. Yeah.
Right. Okay, cool. All right.
Yeah, thank you very much for all the questions.
Yeah. And see you guys next week. Hopefully many of you will be there in San Diego.
Yeah. Oh,
Yep.
yeah. All right. Thank you, everyone. Can you stop the recording?
Yeah. See you.
Yeah, thank you very much.